Okay, welcome back. So today we'll continue our discussion of chaining algorithms, and specifically we are going to look at how do we incorporate gap costs into the chaining algorithms. So let's get started. So as a quick recap, just to remind you that we are looking at heuristics for sequence alignment, and within the heuristics we are currently focusing on how to find a good cluster of exact matches that can be combined together to form a alignment. So we have been looking at chaining algorithms. So in the last lecture we started the discussion of chaining algorithms, where we are trying to look at the cluster of those exact matches that can be joined to form a high scoring alignment. So in the last lecture, for example, we gave important definitions. For example, anchors, we defined a chain, we defined precedence, and we also gave a definition of the chaining problem. And we'll use these definitions for this lecture as well. So if you didn't have a chance to review last lecture, please go and make sure that you understand these definitions for this lecture as well. So in the last lecture we focused on the simplified chaining formulation, where we were not considering gaps, right? So in that case we solved that problem first in order n square time using a simple dynamic programming recursion. Then we said that okay, because we have learned this range maximum query data structure, using that we managed to improve the runtime from n square to n log n, where n is the count of input anchors given to the chaining problem. So from n square to n log n, it's a substantial improvement. However, so in the simplified case we were not considering gaps. The definition of the chain or definition of the problem was simply to identify the highest scoring chain, where the score of a chain is given by the sum of weights in that chain. So if you are considering a chain, then the sum of weights of the anchors is basically the score of the chain. We also argued that because our goal is to identify a cluster of those anchors which will give us high scoring alignments, it also makes sense to consider gaps between consecutive anchors. So for example, if the anchors are far apart versus anchors are next to each other in a closely related distance, then that can matter. So ideally we would like a cluster of anchors where the anchors are very close and next to each other. So for that we said that we would also consider a general version of the problem, where we would consider gap penalties corresponding to the gaps between every consecutive pair of anchors in a chain. So in this case we are also penalizing the gaps between consecutive anchors in a chain. Now how do we define these gaps precisely will come in the next slides, because we are not given the definition of gaps, but intuitively we want to consider the distance between consecutive anchors in a chain. So in this lecture we are going to focus on chaining algorithms while considering gap costs. Specifically we look at two gap cost functions, and we will conclude our discussion on chaining algorithms after this lecture. So the first gap cost definition is called as L1 gap cost. Here suppose you have again two anchors S1 and S2 such that S1 precedes S2. Then observe that the count of characters between anchors S1 and S2 on text T will be given by, so the count of characters in specifically in this gap will be given by S2 dot x minus S1 dot y minus 1. So for example, if this position is let us say 3 and let us say this position is 6, then precisely you have two characters in the middle, that is 6 minus 3 minus 1. So you have, in that case you would have two characters in the middle. Similarly, by the same logic, the count of characters between S1 and S2 anchors on pattern P would be given by S2 dot C minus S1 dot D minus 1. So, these would be characters right here. So, these are the number of characters which are lying between these two anchors on text T and pattern P respectively, right. So, these are the number of characters that lie between the two anchors. Now, in the L1 gap cost, the gap cost will be defined by the sum of these two numbers. So, we will add up these two numbers and compute the gap cost. So, that would be equivalent to taking a sum of this distance as well as this distance. So, with this definition we will proceed forward. So, now intuitively you can think of this cost in the following manner as well. So, for example, suppose you have two anchors S1 and S2 shown here in this example, then the number of characters on the top sequence is 2 and the number of characters in the bottom sequence between these two anchors is 4. So, by this gap cost definition, the gap cost will be 6 in this case, that is 2 plus 4. Now, the corresponding alignment, if we continue to follow the same gap cost definition, the corresponding alignment for this chain would be the first anchor followed by the characters of first sequence aligned to dash characters, followed by characters of second sequence followed by dash characters, and the matching characters corresponding to anchor S2. So, here the gap cost 6 corresponds to doing 6 edits. So, the alignment interpretation of this chain would be right here, where you are basically introducing dash characters against characters of sequence 1 as well as characters of sequence 2. So, in total you are doing 6 edits corresponding to gap cost of 6. So, this is the alignment interpretation of what kind of chain we are looking at, because ultimately what we desire is that the highest scoring chain should also give us the highest scoring alignment back. So, this is the alignment interpretation. Now, how do we solve this chaining problem with this gap cost definition? There is another gap cost definition which is known as L infinity gap cost. In this case, instead of taking a sum of characters on both sequences, we will take a maximum of both. So, in this case, instead of sum, we will take a maximum of both. So, for example, in this illustration, the gap cost will be dictated by the gap on the second sequence, because it is higher than the gap on the first sequence. Now, this is alternative gap cost definition that one can use, and in this case the interpretation would be that if you have two anchors in a chain, then in this particular case gap cost will be 4, considering the gap between two anchors. So, instead of 6, the gap cost will be 4 now, and the alignment interpretation would be that you are basically considering the middle characters between two anchors. So, the initial few characters will be aligned as mismatches, and the excess characters on sequence 2 will be aligned to dash characters. So, here the number of edits is 4, corresponding to the gap cost 4 on the right hand side. Okay. So, this is a slightly better, I would say in practice this gap cost function works better than the previous case, because this is a more realistic representation of the alignment compared to the previous case, because here this is not realistic at all, where you are introducing gap characters for the first few characters from sequence 1 and then gap characters from sequence 2. So, this is relatively more realistic, and this is more aligned with what one would do in practice. So let us get started with how to solve chaining problems with these two gap cost definitions. And to start with, we will start with a simpler gap cost, that is L1. So basically we are solving the chaining problem now, but while considering gap cost between consecutive anchors, and to get started we will be assuming L1 gap cost between two consecutive anchors. Okay. So in terms of solution, how do we solve this problem? Well, the first solution that should come to mind is, if you remember from the last lecture, we have already seen one dynamic programming method to solve the chaining problem. So in the case where we were not having any gap, then we have already seen a dynamic programming formulation which allows us to solve the chaining problem. In this case, basically we started by sorting all the anchors by their y coordinates. Then we said that we will solve the sub problem by filling a array C, where Ci indicates the highest score of a chain ending at anchor Ai. So this is a sub problem in which we are specifically focusing on chains that end at anchor Ai. So to solve for Ci, we had seen this DP recursion, which was valid if we do not have any gap cost. So basically for a chain of ending at anchor Ai, we said that the chain would end at anchor Ai. So we would consider the weight of that anchor, plus we would find out what is the preceding anchor that we should choose, which has the highest score. So a preceding anchor with the highest score can be attached to anchor Ai, and we can extend that chain further by 1. Now this was valid in the case where we were not considering gap cost. Can we modify this algorithm for gap cost as well? Well, yes, it turns out that this modification is easy, because all we have to do is, in the recursion, instead of just looking for the preceding anchor with the highest score, we will just say that we will look for the preceding anchor with the highest score minus the gap cost. So this time we would consider the gap cost between anchor Aj and anchor Ai, and we would subtract that from cost score Cj, right, because there may be an anchor which has very high score, but if the corresponding gap cost is too high, maybe we do not want that. In this case we may consider a less scoring preceding anchor which has maybe 0 gap cost or a small gap cost. So accordingly we would search for the preceding anchor which has a maximum value given by this expression, and this modification suffices to address or achieve an algorithm which also considers a gap cost between consecutive anchors. So now if I am considering all the consecutive anchors for anchor Ai, then I am considering gap cost as well. However, we also saw that unfortunately this algorithm uses n square time, because we are filling a table of size n and each value requires order n time, because computing this maximum requires us to do a linear scan over array C, and as we are doing a linear scan, we are having to spend order n time for this computation. So we want to avoid order n square time, and we can again go back to the range maximum query data structure that we were using last time as well, right. So in the last lecture we had said that these range maximum query data structures can help us achieve faster algorithm, because they offer a mechanism of searching for highest value within a key range in log n time only. So the step that was taking order n time, it is possible to optimize it and reduce the time complexity to log n. So now with these operations, remember that we had optimized the algorithm to n log n using these range maximum query data structures, and this was the algorithm that we had for no gap case, where we had said that we would initialize a tree with d coordinates of the anchors, and we would initially put the values as negative infinity. We will process these anchors in a sorted order, and when we reach the start of an anchor we would compute the score, and when we would reach the end of the anchor we would update its value in the tree. So, this query gave us a log n time method to access the highest score within my range, specified range. So, this allowed me to get the highest scoring preceding anchor because of this range query. So, how do we modify this algorithm to also account for gaps, right? So, in this case, in a way that we are setting a priority of each anchor by its score Cj, and then in the query we are asking that given the range of interest, give me the score anchor with highest priority, right. So, how do we adjust this priority to also account for the gap cost? So, somehow we have to adjust this priority as well. Now, intuitively what may come to mind is, what if we set it to Cj minus gap? Well, there is a issue here, because remember the gap is a quantity that depends on two anchors. So, gap is some quantity that is defined between two anchors. So, if I want to set a priority of anchor Aj, then unfortunately the gap depends on second anchor as well. For example, if I am considering anchor Ak, then the gap would be defined based on the distance between these coordinates. But if I am considering anchor Al, then the gap would be defined based on the distance between these coordinates. So, the gap really depends on what two anchors are being considered, which makes it tricky on how do we set the priority of anchor Aj as soon as its score is computed in the algorithm. So, to address this, we have to observe a property and this property is as following. Consider three anchors Aj, Ak and Al such that anchor Aj precedes anchor Al and anchor Ak also precedes anchor Al. So, you have two anchors Aj and Ak that precede anchor Al. Then the inequality Cj minus gap Aj Al is greater than Ck minus gap between Ak and Al holds true if and only if the second inequality holds. So, first of all, why are we considering this? Observe that if you have an anchor Al, so suppose you have an anchor Al and suppose it has two preceding anchors Ak and Aj, and remember that we would choose between these two anchors based on whether Cj minus gap Aj Al is higher or whether Ck minus gap Ak Al is higher. Because we are considering, we will choose between these two anchors based on these two quantities. Now, what this inequality says is that you can make this choice between these two anchors without considering coordinates of anchor Al at all. So, if you observe in the second inequality, anchor AL is missing. Basically what we want to convey here is that the choice between anchor AJ and AK can be made without considering anchor AL coordinates in this case. So, the proof of this inequality works as following. So, the proof is actually trivial because all we have to do is basically expand the gap cost definition, and as soon as we expand it, it will immediately come out. So, Cj minus gap Aj Al, if you expand it, basically this is equal to Cj minus, so the gap between these two anchors, remember that the way it was defined is Al dot x minus Aj dot y minus 1 plus AAL dot C minus AJ dot D minus 1. So, similarly if you open the second right hand side of this inequality, what you will get is Ck minus a similar expression, and in that case what it will happen is that the terms corresponding to AL will be same on both sides, and once you cancel the AL terms on both sides, you will end up with this inequality because the coordinates of anchor AL will cancel on both sides. And what that basically gives you is that the choice between anchor AJ and AK can be made by just knowing the coordinates of anchor AJ as well as coordinates of anchor AK. So, because of this property, now what we can do is we can go back and now we can set a priority of this anchor AJ without knowing the second anchor with respect to we have to compute the gap. So, we do not need to know the second anchor while computing the gap cost. We can set a priority based on the coordinates of that anchor only, because only these y and d coordinates we need to know and the score of that anchor to know whether that anchor would be chosen or not, right. So, again the significance of the claim is that we can make a choice between anchors AJ and AK without using the coordinates of anchor AL. So, going back to the same algorithm, now we can activate the priority of this anchor. Instead of using score of that anchor, what we will do is we will also add y and d coordinates of that anchor. What will happen is that once we change this priority, when we are making a range maximum query, we will fetch the corresponding anchor which is optimal for anchor AJ. Now, so once that is done, we have to be slightly careful here, is it although we will fetch the correct anchor, the correct preceding anchor now based on the gap cost, but we have to set the score value properly, because the score value is basically AJ dot weight plus Cj plus minus the gap cost, whereas priority we are not including the gap cost. So, we have to adjust the value returned by the range maximum query. We have to subtract the coordinates of anchor AJ to calculate the proper gap cost, because remember that we are in this inequality we are bypassing the need for calculation of gap cost and we are just setting a priority of that anchor. So, once we set the priority of that anchor, we have gotten the priority value returned back to us. So, the range maximum query will return as the highest priority value, and we have to basically adds further terms to that priority value to get the corresponding gap cost penalty as well. So, once we have the gap cost penalty, we are basically correctly setting the value of score of anchor AJ as well. So, this trick helps us to achieve again n log n time, because the time complexity remains same as before. The number of operations and the type of operations that we are doing remains same as the no gap case. So, this small trick enables us to include gap cost in the chaining definition as well. So, now the optimal chain that we are going to output will be considering gap cost between consecutive anchors as well. And observe that all the modification that we had to make in the algorithm is actually ultimately very minor. So, by changing these two lines, we are able to incorporate gap cost in the chaining definition as well. Now, moving to a more interesting case, that is L infinity gap cost. So, in this case we were defining the gap cost between two anchors as maximum of the distances on both sequences, right. So, in this case, instead of taking the sum on both sequences, we are taking a maximum on both sequences, and based on this gap cost definition we want to compute the highest scoring chain. So, now how do we proceed? Well, this case is slightly more interesting, because if you see now, depending on how the anchors are positioned, the gap cost will differ. For example, in the left hand side case, if you consider anchor S1 preceding anchor S2, in the left hand side case the gap cost is being determined by the number of characters on this sequence, whereas in the right hand side case the gap cost is determined by the number of characters on the first sequence. So, depending on how these two anchors are oriented with respect to each other, the gap cost calculation is differing. For example, if we fix the left hand side case, then we can again work out a similar claim like this, and what we will find that is that if we work out the same claim, then we can again set the priority of this anchor in the range maximum query data structure to be this. So, in this case it will be AJ dot D, that is basically the priority of that anchor would be determined by the score of that anchor plus the D coordinate of that anchor, because the more right is the D coordinate or higher the D coordinate, the lesser the gap would be. Similarly, in the right hand side case, if I know that this is the orientation of two anchors, then I would have set the priority of that anchor to be Cj plus Aj dot y, because now the priority is governed by the y coordinate of that anchor. So, higher the y coordinate, lesser is the gap cost. So, normally in that case I would choose an anchor whose score as well as y coordinate is higher. But the question is, we do not know the orientation of anchors. So, as we are proceeding in the dynamic programming algorithm, how do we take care of these two cases? So, how do we do this orientation check efficiently? We can again run the n square algorithm. So, n square algorithm will work, because n square algorithm we naively check each and every anchor, and based on each and every anchor check we can check the orientation as well. But the interesting part is where we have to use range maximum query data structures and enable this orientation check as well. Now, the idea that would help us here would be a multi-dimensional range tree. So far we have used single dimensional range trees where we would give, where our keys would be single dimensional. So, for example, if my keys is single dimensional, I can ask a range within that key and I can pull out the maximum value in that range. But it turns out that the range trees can be used in multidimensional scenario as well, where your keys can be multidimensional. For example, imagine a employee where you are keeping track of a employee by their age as well as their income. So in that case the key would be 2-dimensional, right. So this data structure can be extended to multidimensional case as well, where you can have, for example, a 3-dimensional key, and in that 3-dimensional range you can ask again for the maximum value within that 3-dimensional range. So this time if your dimension of the key is small d, then the time complexity changes now. So for example, for each query the time complexity is log n raised to power d. So for d equals to 1, this is log n for d equals to 1, but for higher values of d this is log n raised to power d. Similarly, the update query also has the same time complexity, log raised to power d, and the time to construct this tree also increases with respect to the dimension. So it is n log raised to power d minus 1 this time. Now how this data structure works exactly we are not covering as part of this course, but we will use this data structure as a result when we are developing the chaining algorithm. So now going back to the chaining algorithm, basically we have to set the priority of anchor S1 properly, but unfortunately we do not know whether the orientation will be either in this manner or whether the orientation of with respect to another anchor will be in this manner. So again I am writing the L infinity gap cost definition here, that is depending on whether this quantity exceeds this quantity, the gap cost will be determined by S2 dot C minus S1 dot D minus 1. Otherwise the gap cost would be determined by the number of characters between the anchors on sequence 1. Because we are taking the maximum of both, that is why either it will be this left hand side or right hand side. I can also rewrite the same definition as by taking this term on the left side and bringing this term on the right side, so that I can write it as that if this condition holds, again we are checking the orientation of these two anchors. So depending on how these two anchors are oriented, the gap cost will be determined by either this expression, otherwise the gap cost will be this expression. Okay. So how do we tackle this now? Because we have not, so far we have seen the range maximum query data structure, we are making a single query in the range tree. So how do we make sure that the correct gap cost is considered when we are making a query in the range tree? Well, the key idea here that we are going to use is we are going to introduce a second dimension to the range tree, and in the second dimension I am going to check this particular inequality. So the first dimension remains same as before, all the details remain same as before, except that we are going to introduce a second dimension in the tree that will check for this inequality. So for example, if this inequality is true, then we know that we have to consider this gap cost, otherwise we have to consider this gap cost. So let us proceed forward. So now we are going to add second dimension to the tree. Another thing that we are going to do is we are going to use two trees. So we are going to use two-dimensional trees. The first dimension remains same as before. So remember that in a previous case also we were using d coordinates of the anchors as keys. So in the previous algorithm right here we were using d coordinates of the anchors as keys. We will continue to do that here as well. Now the second dimension we are introducing, which is to check for this inequality, and again we are adding a second dimension which is the difference of y and d coordinates of that anchor, and we are going to initialize two trees with, initially they look identical because we are initializing them with same set of keys, and all the values are negative infinity. But as the algorithm will proceed forward, we will update these trees differently. So, with these two dimensional trees, let us proceed forward and let us look at the algorithm of how this is now going to work. The key detail that you have to focus on is that the major algorithm remains same as before, that is we are going to iterate over array B same as last time. So, similar to how we did here, we are going to iterate over these anchors in a sorted order. And as we are iterating over these anchors, we are going to make queries in the trees and we are also going to update the tree simultaneously. So, as we are proceeding forward, the only detail that has to be changed now is the second dimension of the tree. Now, through the second dimension, we are checking basically whether we are focusing on this case or whether we are focusing on this case. So, depending on the inequality, we are going to consider that definition of the gap cost. So, for example, if my inequality is being satisfied in this manner, that is my ai dot y minus ai dot d, these coordinates are within this range, then I am going to consider gap cost based on the corresponding scenario. Similarly, if my inequality is satisfied in the other direction, then I would consider the different gap cost on the opposite sequence. And by the same logic, I will set the priority of these anchors in the same manner as well. So, when I am finishing the anchor coordinate, so for example, when I reach at the end of an anchor, then I am going to access that particular key and I am going to set the priority of that key in that order as well. So, for example, in tau 1 tree, I am working under the assumption that this is going to be the gap cost. So, accordingly I set the priority of those anchors based on aj dot d coordinate. For the other scenario, I am going to set the priority based on aj dot y coordinate. So, in some sense, the other way to see this algorithm is that we are again these range maximum queries helping you to look for those anchors which are preceding the current anchor, but you are further filtering down based on the orientation of anchors. So, for example, you in tree tau 1, you will only consider those preceding anchors which are following this orientation with respect to anchor S2. So, with respect to anchor S2, you will only consider those anchors which are following this orientation. From tree 2, you will consider those preceding anchors which are following this orientation with respect to anchor S2, that is the gap on sequence 1 is higher. So, with this criteria and with this trick of using two dimensional trees, we can again address the chaining problem with L infinity gap cost as well. So, I encourage you to review these slides once more because it may take some time to understand how this algorithm is exactly working. But once you understand this algorithm, you will find this very elegant manner, and also you can see that this algorithm pseudocode is so short. So, it is such a simple algorithm. All you have to take care is how the keys are being defined and how the queries are being made in both trees. And this time the time complexity is not n log n but n log square n, because we are using two dimensional trees. So, each operation, each RMQ operation takes log square time and each update operation takes log square time, and that is why the total time complexity is n log square n. Now, to summarize this lecture, we have considered various versions of chaining problem and we have looked at efficient algorithms to solve the chaining problem as well. So, once the chaining problem is solved, all we have to do is basically combine those anchors which are found in a chain and get the corresponding alignment. and this is an extremely powerful heuristic that is widely used in alignment tools. So, coming from the quadratic time algorithms that were used by alignment algorithms, the chaining algorithms really allow us to scale this alignment to very large genome sequences as well, because these chaining algorithms are all using subquadratic runtime. Similarly, finding these exact matches was also very fast. So, as a result, these algorithms scale to very large data sets. And this almost concludes our discussion on chaining problem. I also want to give you one exercise for you to try on your own. So, this is another gap cost definition that is commonly used in bioinformatics tools. Here, this is a slightly revised gap cost function, because here we are considering the difference of gaps on both sequences. So, in this case, the intuition is that if your anchors are all located on the same diagonal, then you would not penalize a gap, whereas if your anchors are located on different diagonals, then you would start penalizing gaps. So, I encourage you to solve this case, and the techniques that are used for solving this are same as before. All you have to do is carefully decide what keys you should set for the ranged trees and how you should be querying your ranged trees properly. And once you do that exercise, you will understand the chaining algorithms properly. So, with this we will close the chaining module, and we will also close this discussion on heuristic alignment algorithms. In the next lecture, we will start discussing genome reconstruction algorithms using graph algorithms. Thank you.